My name is Matthias Niepert, and I'm presenting our work on backpropagating through discrete exponential family distributions. And this is joint work with Pasquale Minervini and Luca Franceschi. Before I start to explain to you the general framework that we are proposing, I wanted to talk about two motivating examples. The first is learning to plan. Here, as an example, we have an input image, and this input image is depicting a map from a particular computer game. And this input image is fed into a neural network, and the output of this neural network is a weight for each small square cell in this map. And what we are then doing is we're taking this output and we're using it as input to a combinatorial optimization problem solver. So in this particular case, a shortest path solver, to find a shortest path that's going from the top left to the bottom right corner in the square here. And then we have a path, and then during training what we do is we are comparing this path with a goal path that's given in the training data, and then we want to update the parameters of this first model here that's after the combinatorial optimization method, which we call the downstream model. But we also want to compute and update the gradients and the weights for the neural network that's up here, which we call the upstream model, which is situated before the combinatorial optimization problem. And that's typically a problem because we need to differentiate here through a combinatorial optimization algorithm that has a discrete output. The second motivating example is the area of what's called learning to explain. Here in this particular example, we have an input text. This is a review of a particular beer. And we are feeding that input text into a neural network. And this neural network outputs weights that tell us something about the importance of the words in the review. So every token in the review is assigned a particular weight. And what we do now in the forward pass is that we are actually sampling discretely exactly k of the tokens. And we are sampling from the probability distribution that's defined by the weights of these tokens. And then we're taking again the sample z. So this is a discrete sample. And we are feeding it into the downstream neural network, which then performs, in this particular case here, the sentiment classification. And again, the question here is, how do we actually backpropagate the gradient from the loss that is incurred here on the right side? How do we backpropagate that gradient information to specifically the downstream, the upstream model here, so the parameters of the input and of the layer X in this particular case. And so that is kind of the question that we want to address. So why is our method called backpropagating through discrete exponential family distributions, even though I've now mentioned also combinatorial optimization problems? Well, that's because quite simply you can turn any discrete combinatorial optimization problem with a linear objective into a discrete probability distribution, where here on the left side you have this maximization problem, the inner product between theta, which are the cost coefficients, and our z. This is a bunch of binary random variables in our case, subject to some constraints. So we want to maximize this subject to z being part of an integral polytope. And this optimization problem can be turned into a discrete exponential family distribution that assigns a probability mass to every z which satisfies the constraints. So the probability of a z is proportional to the inner product between it and the weights here, the parameters theta, and 0 otherwise. And so if we can now find a way to actually backpropagate through arbitrary discrete exponential family distributions, we can also approach this problem of differentiating through discrete combinatorial optimization problems. And that's mainly because we have this correspondence here between the argmax of the optimization problem and the maximum a posteriori state of our probability distribution. So now in the forward pass of a model, and you saw this in example 1 and example 2, we can either take the argmax, so we can have our z be the result of an argmax operation by solving this optimization problem here on the left, or it can be a sample from this probability distribution, or an approximate sample, if it's a complex distribution that doesn't allow exact samples. So let's turn to the actual problem definition and the kind of setup that we are addressing with our work. So here we have an input x. So again, remember this was in our example before, for instance, an image that's fed into a neural network, h sub v. So v here are the parameters of this neural network. The output are some parameters theta, which are the input to this black box discrete exponential family distribution, from which we then sample or compute a map state, and that's fed into a downstream neural network. And then in the end, we are applying a loss function that's typically the expectation, defined as an expectation over the samples from our distribution P, applied to a pointwise loss function to every u, z, and y. And the important take-home message here is that we treat the discrete component as a black box again. So we only assume that the combinatorial optimization algorithm can be executed when given input theta, and we only assume the ability to compute map states of the discrete probability distribution with parameters theta. So the central question is now, how do we compute the gradients of theta with respect to L? So let's look at a particular simple case to get started. When actually, here you can see when our function fu is actually the identity function. In this particular case, we can actually perform maximum likelihood training because we have here a probability distribution from which we sample z, and that's comparable with our gold y's in this particular case. So now we can actually compute the gradients of our loss function by taking the negative log likelihood, taking the gradients of the negative log likelihood, and the gradients of the negative log likelihood are the marginals of our random variable z, so the expectation of z sampled from our probability distribution P here, minus the input y. And to compute these gradients, we only need a way to approximate the marginals. And for this, we will use Perturb and MAP, because remember, our assumption was that we can only compute map states or argmaxes of this black box component here. Generally, maximum likelihood learning, and this is something that will come in handy later in terms of understanding our framework, reduces the KL divergence between the model distribution and the data distribution. And in our case here, the data distribution is just the training data, all the y's that are constituting the training data. Okay, I mentioned again that we are only assuming that we can compute map states of our discrete exponential family distribution. And so when we can only compute map state and we want to sample, what we can do is we can perform what's called Perturb and MAP. So the idea is here that we introduce a particular noise distribution. We are taking our parameters theta. We are perturbing the parameters theta by a sample from the noise distribution. So this is kind of an element-wise addition here. And then we take the map state. And under certain very strong assumptions, you can show that, and for very simple probability distributions, you can show that that actually allows you to sample faithfully from the distribution, from the discrete exponential family distribution with parameters theta. However, in practice, we typically have much more complex distributions where this is just a way to approximately sample. So again, because we are actually having to do local perturbations, so we're perturbing each of the theta i's individually by some Gumbel noise. And here we are proposing a new noise distribution. So typically here we use Gumbel noise. And we introduce here a new, in our paper, sum of gamma distribution, which allows us to also perform Perturb and MAP, and which tends to work better compared to the typical Gumbel perturbations. Okay, so now we know how to sample from a distribution. or even, we propose a way to do it better, essentially with our noise distribution. And we know what to do when this neural network here, f sub u, is actually the identity, so it kind of doesn't exist really. So now, what is the problem, or how can we address this problem when this actually exists, right? So if we actually take our Z and we feed this into a downstream neural network, and we get an output here that might have a completely different shape than our Z, our latent variable Z. So in this particular instance, we cannot use maximum likelihood estimation like in the case before. So the idea that we have here is that because we don't have access to an empirical distribution, right, like in the case of a simple maximum likelihood estimation, what we actually want to do is we want to construct a surrogate empirical distribution, which we call the target distribution. And this distribution is constructed, or can be constructed, in many different ways, mostly by looking at the gradients of the downstream loss functions. But we are proposing essentially in our work two specific classes of target distributions. And one of those classes, which is generally applicable, is the one that I'm introducing here. So this is actually based on what's called perturbation-based implicit differentiation. This was introduced by Domke. Take our original distribution, right? We are feeding our Z into the downstream model. We are incurring a loss. And this loss gives us gradients with respect to Z here. And now we're using those gradients, and we're going in the negative direction of those gradients, to perturb or to change our theta here. So the idea is that if we change our theta by the negative gradients of the downstream loss, we are moving in a direction where our distribution is better at generating samples that have a lower loss. And again, our Z head here, or Z overline, is generated using Perturb and MAP. So let's put all of the pieces together. Again, we have an input X. This input is fed through the neural network. We then get our parameters theta. We perform Perturb and MAP. So again, our assumption is that we now have a combinatorial optimization solver, which is essentially executing the map. Or we have a way to obtain the map state of the discrete exponential family distribution. We are then using Perturb and MAP to generate a sample Z overline here. This one is fed into the downstream model f sub u. And here we have this loss function, this pointwise loss between the output of this neural network and our label y. Then we construct the target distribution q. So here we construct it again using perturbation-based implicit differentiation. So we're kind of moving the parameters of the distribution p here, theta, into the negative direction of the gradients incurred by the loss here. And so this way we construct our target distribution q z theta prime. And then we compute or approximate the maximum likelihood gradients between our p, that is the current distribution, right, of our discrete exponential family distribution, and our distribution q by taking the difference between the map of theta plus epsilon and the map of theta prime plus epsilon. So we use the same perturbations from up here to also perturb theta prime. Now you can think of this as taking one sample from P and one sample from Q, and now we are taking the difference of those samples. That's what we use as an approximation to the gradient of theta with respect to the loss function. We compared our proposed framework with several existing methods that are typically based on relaxations and obtained very good results in the learning to explain sentiment scoring problem that I also explained earlier. We also compared IMLE to the straight-through estimator and the score function estimator in particular different settings. And if you're interested in the experimental results, please take a closer look at the paper. And then finally, our code is available in 2 repositories. We have it in TensorFlow 2 and also PyTorch, and it's very easy to use this as a layer in a standard deep learning architecture. So thank you very much for your attention, and please reach out to us if you have any further questions.